The James Webb Space Telescope is challenging much of what has been accepted as truth in cosmology over the past few years, according to Durham College teacher Carlos Plain. I spent my entire life fostering a specific hypothesis of the universe, and presently the hypothesis is being tested. I welcome that since that is the manner by which we push ahead, that is the means by which we gain ground in science. Another ultra-deep image demonstrates our cosmological mistakes. The telescope, which was supposed to reveal the universe's initial stars, is now working against historical perspective and might introduce us to a completely new field of study. Many academics welcome the results since they have long been certain that something was wrong with our previous theories. Thus, not all analysts are shuddering in horror at the new facts. When it came to correctly understanding the warnings, scientists persisted to their old theories, even though the differences in estimates of the universe's expansion rate alone should have shattered their conscience long ago. About 380,000 years after the Big Bang, when the cosmos had cooled sufficiently for protons and electrons to combine to form stable hydrogen particles, the cosmic microwave background radiation, CMB, which is regarded as the most well-established light in the universe, was created. This development, which analysts refer to as ionization, allowed light to penetrate the universe. American scientists Robert Wilson and Arno Penzias discovered the CMB in 1964 while working on a different kind of radio antenna technology. This finding, which earned Penzias and Wilson a Nobel Prize and a permanent place in astronomy history, was long considered to be one of the most solid pieces of evidence supporting the Big Bang theory. The CMB probably provides a sneak peek at the early cosmos, with minute temperature differences revealing important information about conditions just after the Big Bang. Among other things, researchers used the CMB as a tangible record of the fundamental measurements of the material world to determine the rate of expansion of the cosmos. This was previously established in the late 1920s by the astronomer Edwin Hubble, who discovered that distant cosmic systems move away from us in all directions, and that their speed corresponds to their distance. These observations are now referred to as the Hubble steady or the Hubble regulation. Hubble's extension rate was recalculated to be far lower than Hubble's unique number since it lacked the high-level estimating tools that were available several years after the discovery of the CMB. Using Type I supernovae as standard candles, later researchers recalculated the rate again, providing consistent light that could be used as a reliable estimate point. The CMB estimates produced an expansion rate of about 67 kilometers per second per megaparsec, whereas supernovae estimates produced an expansion rate of about 74 kilometers per second per megaparsec. What does this difference actually tell us about the universe's rate of expansion? Did you know that since the 1990s, people have been aware of this error? Since then, scientists have been aware of or speculated that there might be a problem with the CMB's evaluation, estimation techniques, or the idea of the universe's expansion. Scientists refer to this discrepancy between the many projected upsides of the expansion rate as the SAA pressure or Hubble pressure. The implications of this strain are enormous, indicating that important aspects of our potential universe interpretation may be flawed. Experts were perplexed for a long time. Since it began operating, the James Webb Space Telescope has given scientists incredible data that could help them understand the problem of the universe's rate of expansion. Old astronomy is being overturned by systems so old and developed that their growth should, in theory, have begun before the Big Bang. Scientists now discuss the biggest urgency in modern stargazing rather than faults or estimation contrasts. The entire idea of development or the Big Bang itself is being discussed, in addition to the possibility that the expansion rate is incorrect. Photographic networks provide evidence of a universe completely different from what we have long believed. The first warning came from the SAA. Experts who continue to believe in outdated theories now face the question of whether we actually know anything about the cosmos. Standing on the wreckage of their labor of love, many scholars explore space in dread, having finished absorbing what they discover. We need to examine ourselves what we actually know about the universe in light of the scientific emergency. We must understand the workings of science in order to respond to this. To move from the broad to the explicit, hypothetical researchers employ a complex network of numerical models, precise data, and logical reasoning. They draw their understanding from a combination of observations, oddities, experimental findings, and theoretical analysis. Just the word hypothesis indicates that these are ideas and constructs rather than definitive revelations. Our only reliable sources of knowledge are the images provided by telescopes, the radiation and sound waves captured by radio telescopes, and the most recent data from gravitational wave detectors or neutrino estimation systems. We currently have a tool that can break down the most well-known light into its component frequencies and analyze it in amazing ways thanks to the James Webb Space Telescope. Webb can reveal the most common elements found in worlds that existed before 13 billion years ago, as well as their mass and star count. It is also capable of reproducing the form and evolution of a world. In any case, Webb may also have flaws. For instance, it is unable to consistently determine with certainty whether we are witnessing worlds or shadowy apertures with massive accumulation circles that gleam as brilliantly as a universe. We have to face the fact that modern science has long rejected optional explanations and accepted an overwhelming number of alternatives as insights. For a long time, research has been certain of its accuracy. As has frequently happened in science, the most recent findings from the James Webb Telescope are crucial cues to replace conjecture with fresh understanding. Researchers are currently holding up. Many analysts struggle to provide fresh explanations, and the latest discoveries are too shocking. The latest findings frighten many experts and upend the fundamentals of our physical science. The majority of physical science classes today are still based on Isaac Newton's 17th century investigation. For hundreds of years, our true understanding of our current world and the universe was based on his laws of motion and gravity. Newton's laws explain how things change under normal circumstances and work well on Earth, but in space, his ideas needed to be expanded upon, which Albert Einstein largely did at the beginning of the 20th century. Published in 1905, Einstein's unique hypothesis of relativity upended our understanding of reality by proving that all of them are comparable and dependent on the growth of the eyewitness. With numerical proofs of gravitational peculiarities in light of the bend of spacetime by masses like stars or universes, his general hypothesis of relativity, published in 1915, expanded on this concept. Einstein's rules and ideas were relevant in many fields, but he also saw where they fell short. He yearned to envision a world equation, but he was unable to do so since he realized his conjectures could never fully capture the universe. To yet, no other specialist has succeeded. The step is where? Isn't it intriguing to find out where it is? In a conference, renowned American astrophysicist Michio Kaku stated that solving this problem will surely earn a Nobel Prize. Why don't we look at if our telescopes are to blame or whether scholars might have overlooked potential misunderstandings? When it comes to the real causes of the cosmological emergency, dark matter and dark energy are the top suspects. Our current universe models include the notion that dark matter and dark energy comprise around 95% of the universe, but neither has been directly observed, and their actual existence has never been proven. They may have features we don't yet understand, or they may not exist at all, requiring different explanations for the evolution of the cosmos and the dynamics of systems. One theory is that dark matter and dark energy have evolved throughout time, maybe displaying intelligence of some kind. Another concept that should definitely be tested is gravity. It has not yet been shown that this ability can create curiosity through mass or bend in space-time. In any case, we cannot rule out the possibility that gravity has surprising qualities compared to our initial assumptions, or that another influence is the cause of the gravitational pull between objects. Einstein is commonly credited with developing the ideas of the space-time arch, which have been validated experimentally. A few attributes have been established as infinite constants in astronomy and cosmology throughout the long run. From early human innovations that saw the stars to modern space telescopes that probe the depths of the cosmos. The study of the cosmos has always been a journey distinguished by our unwavering quest for knowledge and understanding. Every advancement in theory and innovation has revealed fresh information, and tests have confirmed established beliefs in the field of cosmology. The James Webb Space Telescope, JWST, promises to alter our understanding of the origins and evolution of the universe and serves as a beacon of our logical progress. Launched with unique capabilities, JWST marks a breakthrough in observational space science and is ready to probe the depths of reality like never before. Studying the cosmic microwave background, CMB, radiation with unparalleled precision is one of JWST's primary goals. Often referred to as the glimmer of the Big Bang, the CMB provides a glimpse of the universe just 380,000 years after it was first introduced to the globe. Understanding the evolution of worlds and large-scale structure requires knowledge of the universe's fundamental circumstances, including temperature variations, which are conveyed by this artifact radiation. One persistent problem with suggesting a slower rate of cosmic expansion is the mistake in the intentional upsides of the Hubble constant, sometimes referred to as the Hubble pressure. A greater value is obtained via cosmological testing and observations using Type I supernovae. The strain implies that there may be gaps in our current theories or crucial aspects of the physics of the universe's expansion that we are still unable to understand. JWST may help solve other cosmic mysteries, such as the nature of dark matter and dark energy, in addition to the Hubble pressure. These complex components are thought to make up the majority of the mass-energy content of the universe, but their existence is still indirectly produced by gravitational impacts rather than directly observed. The ability of JWST to focus on the distribution of matter and energy throughout cosmic history may provide crucial insights into the characteristics and evolution of dark matter and dark energy. Furthermore, JWST's observations of distant cosmic systems and celestial populations provide a fleeting glimpse into sweeping tales that were already far off. Stargazers can track the evolution of stars and cosmic systems over billions of years by examining the light from extinct worlds. These observations not only help us better understand the structure of cosmic systems, but they also offer insights into the mechanisms behind the development of the early cosmos. The high-level instrumentation of the telescope, such as its arrangement of spectrographs and infrared locators, enables scientists to investigate the material organization of distant objects in remarkable detail. JWST can unravel the cosmic history of substance augmentation by measuring the overflowing of elements such as hydrogen, helium, and heavier metals in old star-forming localities. These facts are crucial for establishing models of celestial development and comprehending how the attributes of universes have changed throughout eons. The ability of JWST to identify and characterize exoplanets, planets orbiting stars outside of our local planet group, is among the mission's most intriguing features. JWST can study the atmospheres of these distant worlds and look for signs of tenability or even life by observing the faint infrared light they emit. This capability represents a significant advancement in our quest to identify potentially habitable worlds and understand the diversity of planetary structures across the cosmos. JWST aims to demonstrate global coordinated effort and mechanical development in addition to its logical objectives. NASA, the European Space Organization, ESA, and the Canadian Space Agency, CSA, were among the space agencies that committed to the telescope's advancement, underscoring the global effort to push the boundaries of space exploration. JWST embodies years of research and design expertise, from its complex sun screen design to protect sensitive instruments from sunlight-based radiation to its state-of-the-art optics tuned for infrared senses. There have been difficulties along the route to launch JWST. JWST, which was first envisioned in the aftermath of the Hubble Space Telescope's success, had specific challenges, funding needs, and delays that tested the resolve of scientists and experts working on its advancement. In any case, perseverance and ingenuity won out, and in December 2021, JWST successfully launched atop an Ariane 5 rocket. Currently operating in its designated orbit near the second Lagrange point, L2, approximately 1.5 million kilometers from Earth, JWST is prepared to embark on an unprecedented exploration journey. JWST's infrared capabilities enable it to penetrate thick residual clouds and detect objects obscured from optical telescopes, unlike its predecessor, Hubble, which mostly operates in bright and invisible frequencies. From close infrared to mid-infrared districts, this unique viewpoint provides a comprehensive view of the cosmos over a wide frequency range. The academic community eagerly awaits JWST's initial light observations, which are expected to reveal a wealth of new information and tidbits of information on important questions about the cosmos. For years to come, JWST's observations will influence how we might understand astronomy, cosmology, and planetary science, from studying the conditions of the early cosmos to focusing on the surroundings of exoplanets. Astronomers will be able to focus on anomalies ranging from star configuration in nearby systems to the development of supermassive black holes at the centers of distant universes thanks to JWST's ability to capture high-resolution images and spectra of celestial objects. JWST will provide crucial information to test and improve theoretical models of cosmic cycles by settling minute details in galactic objects with remarkable clarity. Our understanding of the life cycle of stars, from their organization in dense atomic mists to their potential demise as supernovae or heavenly remnants, will also be improved by JWST observations. JWST will shed light on the mechanisms governing star creation and the influence of the environment on heavenly growth by observing heavenly nurseries and star-forming districts across different systems. JWST's logical mission is further supported by the exploration and development of universes. JWST will track the evolution of cosmic formations and their progression into the different clusters of universes observed in the universe today by observing the fundamental characteristics, components, and complex structures of systems throughout infinite time. These observations will yield tidbits of information on the tools responsible for shaping cosmic systems, such as interactions, feedback mechanisms from star formation, and the formation of extremely large black holes. JWST's capabilities extend beyond standard astrophysics analyses to include fundamental questions like the concept of space-time and the origins of the cosmos. JWST will contribute to our understanding of the vast scope building of the universe and the secret material science that controls its layout and development by observing gravitational lensing impacts and investigating the transport of dark matter across astronomical scales. Perceptions from the telescope will also help interdisciplinary research efforts, such as the search for extraterrestrial intelligence, SETI, and the study of the organization and sustainability of planetary systems. JWST will offer crucial information to answer one of humanity's most important questions. Are we alone in the universe? This will be accomplished by examining the complex syntheses of extraterrestrial habitats and searching for biomarkers typical of life. Furthermore, there is nothing more important than JWST's contribution to inspiring future scholars, experts, and space travelers. People all throughout the world will be captivated by the telescope's remarkable revelations and inventive achievements, which will encourage them to pursue careers in STEM sectors. For many years to come, JWST will leave a lasting legacy of logical achievement and research by fostering curiosity, creativity, and a passion for learning. JWST serves as a testament to humanity's tenacious spirit of inquiry and discovery as it embarks on its primary mission to unravel the secrets of the cosmos. From its state-of-the-art equipment to its aggressive rational objectives, JWST is a triumph of global collaboration, mechanical advancement, and rational creativity. JWST will expand our expansive horizons, deepen our understanding of the cosmos, and motivate future generations to continue pushing the boundaries of knowledge with every observation and discovery. All things considered, the James Webb Space Telescope is dedicated to transforming our understanding of the cosmos and revealing fresh insights into its origins, evolution, and key characteristics. JWST is a reference point of logical advancement and a demonstration of mankind's interest, constancy, and mission for knowledge by pushing the boundaries of observational space science and advancing our innovative capacities. JWST is prepared to unlock the mysteries of the cosmos and inspire future generations to explore the wonders of the cosmos beyond our most breathtaking dreams as we await the revelations that lie ahead.